Okay, just so you know, the video that I'm about to show you is just an example. You need to pick 5 energy transitions. That's like 5 different situations on the OK Go, this too shall pass. That's what gets you your junk box tomorrow. Okay, just really quickly, in case you don't want to know, a lot of people were finding it useful to slow down the video. So if you go to settings, it's a little bit different on your phone, but if you go to settings, if you go to speed, you want to go like up here. Down here, this is faster. Up here, that is slower. So I'll put this in full screen and let's watch. Okay, right here is where I'm choosing to start to watch this. So what I'm going to do is, let me bring up the other page. Okay, I paused it right here and I'm going to go zoom in on square one right here. Okay, and here's what I've drawn. I have drawn this situation. You don't have to draw the jar or anything else. I drew the yellow ball. That's this right here. And I'll put the time in a circle, 0.04. And then I labeled this yellow ball. And I'm going to use for the subscript of yellow ball, YB. And I put height that says YB. And it's above the earth because we know there's going to be gravitational something happening because it's going to fall. So I've done all of that. Okay, so if you look, I also added that right now, I'll show you this. This is technically at rest at the split second that I'm looking at it, the yellow ball. So I put the velocity of the yellow ball is 0, it's at rest. And since I have some height above the earth, and it's not moving, the only kind of mechanical energy you're going to have is gravitational potential energy of the yellow ball. Okay, the next part of the video is a little weird, but remember, there are no outside forces. That means there's no friction. That means that, yeah, it's kind of strange what happens. So watch the video. Sorry, okay. Yeah, there's the yellow ball. Okay, this is actually a very, very not so steep ramp. So it's going down there, and that's still considered a ramp. And this is considered a ramp. So basically, it rolling along the ramp like that, you could just consider this one big ramp because it kind of circles around. You could just consider this one long ramp. Since it has no friction, it does not matter which way it twists and turns. So since all of this potential energy from the height of the yellow ball got transferred to its kinetic energy on this allegedly assuming frictionless ramp, it got transferred to regular kinetic and rotational because the ball is rolling. I'm just going to start looking at it at 8 seconds right here. So this is going to be where we start looking at it. Okay, again, we're going to watch this on the frictionless ramp. I'm going to start looking at it at 8 seconds. Let's slow down. Okay, right there. Let's watch what it's doing. See how you've got just a little bit of height? What I'm doing is right here to right there. Just a little bit of height this way because I'm considering this my 0 mark right around in here. So you've got just a little bit of height of the yellow ball. So I've called that height yellow ball prime to not confuse it with the original height that the yellow ball dropped out of the jar. Okay, and if you'll notice, the ball is actually rotating and moving forward. I exaggerated the steepness of this ramp. Okay. It's rotating and moving forward. So I'm looking at it this 8 seconds right before it hits this whatever pencil thing. So this is what I have. It's rotating. This is omega. It kind of looks like a butt, like spin your butt in a circle. It's the last letter of the Greek alphabet. So this is the omega, how quickly, or the angular velocity of how quickly the ball is spinning. And the ball is also moving forward, and it's got a certain velocity. If we just follow the center of mass, it'd have a velocity going with the direction of the ramp, which again isn't this steep. That height and the gravitational field of the earth acting on its mass or its weight or what's pulling it or what's acting on it. So let's do the energy on this one. All right, so what I have is we have a new potential gravity due to the height of the yellow ball and the Earth, which causes the gravitational field. So we've already written one potential energy due to gravity of the yellow ball, and this one, since it's the next one, I'll just put prime. So it means after. Plus, it's rotating. We have the angular velocity here, so we have k rot, rotational kinetic energy, the yellow ball, still going in a straight line. So that is k kinetic energy of the yellow ball. And this is an extra line here. So that's your first thing. And since you have an ideal system, these two things are actually equal to each other because there's no outside forces and mechanical energy is conserved. So all of your potential energy here, which was your mechanical energy that was involved when the ball was in the jar, got converted to it being at a different height and rotating, and also having a speed forward, kinetic energy forward. Do one more. Okay, so at this point, the ball is going to come here and hit this hammer, and that's actually the point I considered 0. So if you went from like the point where the ball's going to be right here to here, there was just ever so slightly a slight slope. Anyway, when the ball actually hits this thing, I'm going to say it's at 0. Right there. So actually, I'm going to go back just a little bit further right before it hits it. Just like the split second before that. So we're going to say 9 seconds. And this hammer, when it was kind of pushed forward, it actually had, think about having your hand there, like right here. Why would it hurt? Well, gravitational force would be acting on the hammer to make it want to swing back. So that would be a potential energy due to gravity. All right, so this is what I've drawn. Let me zoom in a little. Sorry. Okay, so basically, since this ball's reached what I considered the 0 point, it doesn't have any potential energy due to gravity anymore. It's still got your angular velocity and the velocity going straight ahead. And now you have the hammer. And the hammer is just a little bit up above the Earth. So that gives it just a little bit of gravitational potential energy. One more quick thing. Since you already had these two, the angular speed and the angular velocity and the regular velocity up here in part 2, I'm going to add one quick thing to kind of differentiate these down here. Let's just make these prime so that we know that they're after the last ones. You don't have to do that. Those are supposed to be primes. Don't have to do that with the hammer because that's a new thing we're introducing. All right, so let's pretty much finish it up. I have the potential energy due to gravity from the hammer's height above the Earth, and I should have put prime on these two. Then I have the rotational kinetic energy. The yellow ball's still rolling and it's still going forward, so that's its regular kinetic energy. And what I can do is go up here, and that's kind of awkward because you kind of go to another row on the page. But this is actually 2, since mechanical energy is conserved because there's no outside forces, therefore it's an isolated, also known as closed system. See, this, your potential gravity of the yellow ball when it starts off, is equal to the next potential gravity of the yellow ball, potential energy due to gravity of the yellow ball, plus the rotational kinetic energy of the yellow ball, plus the just regular kinetic energy of the yellow ball. And again, no outside forces, isolated system, therefore mechanical energy is conserved. This mechanical energy just gets converted over here to potential energy of gravity due to the hammer, plus rotational kinetic energy, the next rotational kinetic energy of the yellow ball, plus the next regular kinetic energy of the yellow ball. That's a lot to say. That's why symbols are easier. But basically, you just have your mechanical energy being converted to different kinds of mechanical energy because it's an isolated system, because there's no outside forces acting on it.